Okay. Hello, fellow 4, 5, maybe 6 F# developers out there. Nice to meet you guys. It's Friday, another F# amplifying F sub session. As always, a small recap of last week. We had Jindrik working on Wider. He improved the auto completion for custom operations and CEs. And yeah, we made some really good progress. You can check out the PR. It's open on GitHub, not merged yet, but yeah, we hope it will be reviewed and merged soon. And it will really improve the user experience for all CE users out there. So yeah, shout outs again to Jindrik for tackling this issue. If you would like to do like Jindrik and have a session with us, check out our page. It's amplifying F# GitHub.io. Get in contact with us via the socials or on Slack, Discord. Yeah, you will find a way to get in contact with us. And yeah, we are happy to have more people here. Also, people who have done already a session in the past are very welcome to do a second session or a third session. And this leads us to Houston, the champion of today's session. For a very first time, we will have some hardware in the show. And yeah, I'm very happy to have him. It will be super interesting. And yeah, I give it up to Houston. It's all yours.
Thank you so much. Hi, everyone. I am going to be switching through a lot of different screens, as you can kind of see in the background here. I've got two workbenches that are just in an absolute disarray, and my computer screen is the same way. So I'm going to my eyes will be moving around the screen quite a bit as I show different things. The main topic is talking about the positioning of a solar panel and the calculation process that I went through in order to be able to do that accurate calculation. So there will be a little bit of a scientific digression. There will be a lot of talking about how the work is being done on the edge processor. And then, of course, eventually working our way out into zooming out into this, the interesting thing that's happening within F#, which is using LMesh everywhere as a standard pattern. And one of the things I wanted to do is use LMesh on the edge device itself so that it's managing these thread safe little pockets of both messages, inside the loop, and then commands out for all the side effects. And I got a lot of support from that from different groups, and some of them I'll be doing some name dropping here along the way. First, I want to talk a little bit about myself and kind of where I come from and my background. And this is for those that didn't see like any of the other presentations that I've done. I'll just do this very quick little vignette. This is two reasons for showing this photo. One is the picture in the middle actually shows this enclosure over the top of a Lotus Labs Meadow board. That was the original experiment for moving CO2 through the enclosed space. And this, I'm continued the experiment with volatile or organic compounds, and I'm using evaporating isopropyl alcohol as the trigger to trigger the sensor. So this is kind of an ongoing project, but it's matured not only in terms of changing the way the sensor is behaving and what things I'm pulling off of the sensor, but also I'm now using an LMesh loop for managing the state of the sensor and the microcontroller and all the things that it's doing for updating the display in the side effect world. There's another interesting thing about this photo that's above my talking head. Sorry, you have to see my face 3 times on this thing. That's so weird. But there's a photograph there with Bob Moog, who is my mentor and research professor, who was also my advisor and eventually became my first boss. That photograph is back when I had hair. And I'm sorry.
Do you want to share your screen, or do you want to stay like this?
I am sharing my screen. I'm sharing.
Okay.
So the problem with this setup is it has all of us on the YouTube stream, and so the only way we can get you to have like full screen, I think, is to have you share your screen. I think that's the way it has to work.
Let me see if I can.
Unless
all right. Let me share
the camera as well, like kind of.
Yeah, I'm trying to share the camera. position. Let me see if I can get that done. Share sound.
Well, yeah, David, if you try to make it like full screen on your end, I wonder, since you're the one recording, I wonder if it'll go for that. So if you like choose him as the primary person, like you,
It's good. Could you repeat? What do I have to do?
I think if you like, so like when you click, there's like the view, and you can go to the gallery or the speaker, and it's like in the upper right of like the chat window.
Oh, okay. Yep.
See if you can go to that, and I'll see if it looks fine on YouTube. If you choose, try to make it like full screen on yours. Let's see if it changes. If not, we may have to have them share a screen. Sorry for the technical difficulties, everyone. Technology is hard.
I don't know how to pull this off.
In the like top right, do you see like the view?
Yeah, I'm in full screen, but
Can you click like there's gallery and speaker? I don't know if you can see that at all.
yeah.
If you click speaker, I don't know if it full screens it for you essentially.
No, yep. Houston should be the speaker if he continues. Yeah.
Okay, so if I take over the mic, maybe it switches over to me if you're still doing live switching. So can you see I'm in the lower right-hand corner, and there's this static slide with images kind of splashed all over it. That should be what you should see.
This works. This works.
Yep.
Yeah, so I'm switching back and forth between the different positions in OBS. So in this photo in the upper, I guess you could say upper right-hand corner of the screen, there's this older photo from the 90s. So Bob Moog, myself, and the first person that I hired, who was a classmate of mine. But the most important person in this photo for the purposes of IoT and Edge is the person who took the photo. And that's Rudy Linhart of Lyntronics and also Music House Tomont. He, in the 90s, built a lot of the microcontroller technology that allowed analog synthesizers to be able to work in the MIDI and digital world. And he was the person that actually showed me how to, build interrupt-driven software within the Zilog Z80 processor to be able to drive synthesizers. This was both for the memory Moog and the MIDI Moog synth. So it's not just the photo that's there, but also the person that's taking the photo that's really important. And I wanted to give a shout out to Rudy. The other reason why I wanted to show this photo is in the center here is this image of the enclosure over the circuit board that has the early prototype of the Meadow board running a CO2 sensor. And it's actually a composite sensor that can pull volatile organic compound values as well as CO2. It's a little cheap $10 sensor that's not clinical, but it definitely gets the job done. And I'm still using that kind of sensor here to look at VOC, and we'll look at the code for that. So this is that board. And I want to go ahead and at least show, show something working. And that way, when we actually look at the code, we can understand that this is more than just an academic exercise. So what I'm doing right now is I'm putting some rubbing alcohol on a Q-tip. And then you'll see I'll put this right over the sensor. And what will happen is, even though isopropyl alcohol is not a volatile organic compound, it kind of registers on the sensor because it's a cheap sensor. So now I'm going to take that away, and hopefully I won't leave too much lingering alcohol vapor there to make it run too long. But essentially what happens is, once it goes over threshold, the relay turns on, and of course the sensor is updating every 2 seconds. In a real world application, this would be every few minutes to maybe every 15 minutes. And the sensor behind the scenes would still be taking readings and pulling that and pushing it aside. But here, for the purposes of a demo, I'm running a very tight loop that just runs every 2 seconds. And so the display itself is, of course, updating numbers of what the previous and what the predicted number is, and the direction of, whether or not the values are going up or going down. And then the lights that are coming on both for the relay and for the board is basically for that indication to show that, oh, hey, we should be running a fan. So if I was actually running it in the enclosure, those fans would turn on, and it actually would take and move the fouled air out and put fresh air in. So this was, of course, started with COVID-19 times, and has now moved to an application where we can take and put this board inside of a place where, like, you're doing resin-based 3D printing, where the actual compounds that come off of that process actually are volatile organic compounds, and you want to measure for that and mitigate and maybe circulate the air for that. So now it's gone down below threshold, which is I believe I set to 35 or forgot. Anyway, we'll see it in the code in just a minute. So once it goes below that threshold, then the relays turn off and the fan stops running. So the idea is it's responsive and reactive to the environment, where it only is running the fan and running your ventilation system when it's actually needed. These values are a little bit arbitrary, but the basic idea is to have this sensitivity to measuring what's happening and displaying it so that a user can look at it, and then also having the conditions inside of the sensor to be able to handle that side effect of, oh, I want to throw this relay, or I handle the side effect of, oh, I need to make a change to what the color is in the display. So we'll talk a little bit about that here. You can see that this is, of course, running in F#, and the background, but all the backing for this, it actually allows us to happen is the Meadow Foundation and the peripheral support and drivers that are written by Wilderness Labs. That's all done in C#. So this is a .NET thing more broadly than just F#, but this is F# access into the world of the edge devices with as designed by Wilderness Labs. So you'll see units of measure here that's a little bit explicit, where, and of course you really can't, oh, maybe you can actually see that. Oh, good, you can. So this is all, code that's been, pre-written that's for different purposes. And so they have an entire library that's nothing but a units library, and it's for nothing but managing all the different units of measure. And this is important in this case, where I went from the VOC sensor, where everything is measured in parts per million, to everything is actually measured in parts per billion. So it matters in terms of like the actual efficacy of the sensor itself. And it also matters for what you're displaying in the display, so that, whenever you're taking and converting this value, that it doesn't show up as a 0.00001, it shows up as a 1, because the units of measure have actually, moved the decimal to the right place, and it gets shown as an integer value. So here, the basic idea is just to create I guess you could say a kind of a limited case, and these values that are set for what is the trigger threshold and the reduction threshold and the nominal value, those are all arbitrarily set by myself. And what I planned on doing was, of course, going and looking up how other sensors behave, particularly things that might have more of a clinical kind of application, and find out what thresholds they have and like what color banding they do, so that it comports with the types of things that people see. But for now, the idea was just to see the mechanism work and just throw it over. In the LMISH model, the only three things we really care about here is the latest and the previous and the projected value, and all three of those things are displayed on the screen. And then whether or not the ventilation is on. And that's controlling a relay on the micro processor to be able to throw the relay in and switch the power on the fan. We have one message, which is basically setting the VOC values, and then the initialization, which is setting everything to nominal. With the VOC, the nominal level is 0 parts per billion. In the measurement of carbon dioxide, the nominal level is 400, because that's the amount of carbon dioxide that just naturally occurs in air. So the sensor that is here doesn't really care about anything any lower than that. When you get into clinical sensors and things that actually do like measure in a vacuum, like breweries and some other clinical environments, where they want to be sure that the absolute amount of CO2 that they are measuring is exactly the amount that they want in a particular application, they use a different style of sensor. But for the purposes of this, it's good to get an off-the-shelf thing from Adafruit and just throw it in and look at the values. You'll see here is the update function that manages all of the activities behind the scenes. There's two things that we're really looking at doing, is figuring out what is the new value. Of course, we get a new reading off the sensor that's running on an observer. And then also taking the old value, and then we're doing some logic to basically say, do we have something that means that we need to turn on the ventilation? So there are three factors that are involved in that, which is one, if it's absolutely over the threshold. And then two, if as it's coming down, but it's still over the threshold, is the ventilation still on? If the ventilation is still on, we don't throw another message out to turn the ventilator on, because it's already there. So there's a couple of controls in there that are logical processing that's very I guess you could say garden variety, the perspective of we've got this loop that runs selectively whenever the conditions arise. So in the run function, we actually have all the, probably some things that need to be in the initialize, but I was kind of being a little bit fast and loose with this. So we're creating the actual I2C bus, which is like a USB, but it's for microcontrollers. It's basically just a serial bus that has, you know, a signal line going to and from the various devices that each have their own address. Initialize the sensor and then the RGB LED, and then go through and actually set up the SPI clock configuration and do some specific things with creating the bus and then initializing the display. So all of this is just handing over a bucket of, I guess you could say, default parameters into the underlying Wilderness Labs code that really is doing the housekeeping for you. So that's one of the really nice things that this feels, it doesn't feel like low code when you're talking to an edge device, but this is about as close to low code as you can get because a lot of that underpinning work has been done by Wilderness Labs. Now the beginning of setting up the logic for how you're going to write to the display. And this comes back to this thing of the display having 240 pixels, you know, width and height, but it's also a circle. So you don't really get all of those. So you're actually going to be writing out to the edge of the circle and then to a certain degree, kind of ignoring everything outside of that. So there are certain things within this that you're doing that's kind of a pro forma activity that, so if you're basically telling the driver that if for some reason you're writing a pixel that doesn't actually have a place on the display, to not throw an error and to not cause a problem, just to ignore it. In the case of the way that I'm writing the canvas, it's never writing a pixel outside of that circle area, but there's some safety that's built in there so that if you're just taking and throwing images or polygons or text into that display area of the device, that it can safely display an area where it can, and where it can't, it just ignores it. So, so this function here is the one thing I think is probably the purest F# function that gets used multiple times, which is when you fall over a certain value coming in from this new value in the observer, to then evaluate for it. And if so, then we're setting the colors for the different numerical values that are displayed on screen, as well as those little circular bands. In the real time, and with the camera, the color space of the camera that's over the top of this device doesn't really show that camera, doesn't show the color contrast very well. You're going to have to kind of trust that it's there. And when you're looking at it with the naked eye, it's readily apparent that when something goes from blue to that orange kind of smoggy color to red, that you know what when you look at it at a glance, you know what you're seeing. And of course, the arrow moving up and down also gives you an indication of where it's going. And the purpose of a 2-second loop, that's kind of a little perfunctory, but if you're sampling the values out of the atmosphere every 10 or 15 seconds, but you're actually updating once every couple of minutes, you can actually have that arrow have a little bit of nuance to it based on what it's seeing over the interval that it's actually updating the display. So this is common in a lot of applications, but for the purposes here, I'm just running a very tight loop. So this is the really the update function, which is update display. And this is the main, I guess you could say, side effect. And this is building a canvas and then drawing all of the circles and all the numbers that you saw happening on screen. So
Lucien, is there a chance that you somehow maximize the resolution of this stream here from your end?
I think I'm running at 1080p. Is it blurry?
Yeah, it's a bit blurry.
Let me see if I can set my camera resolution. Output type. I thought I had set it already to be at least, I can share a 4K screen, but I didn't know if people wanted to look at all the detail on a 4K. Settings. Let me see if I can set the virtual camera on the output and make sure that it's streaming. I'm just going to up the video bitrate and see if that helps.
Yeah, I've
apply.
The font is just a bit blurry, but yeah.
Yeah, no, it's weird. It seems like it's only VS Code. When I look at it in Visual Studio, it seems to be fine, but let me know.
Oh, okay.
So
Okay.
I don't know why that is. There's some resampling in this particular image, and I tried to get the resampling out of it. Let me just do a quick capture method is automatic. Let me just see if I can set that to. So I changed. See, that's even worse. That's just not. I don't know what's going. I can see that. Let me just do. Yeah, I don't know why that is for Visual Studio Code. I'll be away from this in a few minutes. Visual Studio is
Yeah.
better.
Okay.
Working at the other project.
No worries.
So anyway, there's the update display function, and then there's the toggle ventilator function. So those are the two that are happening. And then the subscription is actually the loop that runs that is pulling values from the sensor and then seeing whether or not it actually is a difference. If it's a difference, then it goes through and does all of the updates. And of course, here's the Elmish run for it. So the for me, the important thing of this is that it's kind of like an advanced hello world. You're running one sensor and you're running it on one display. And so this is that Elmish proof of use that you can run Elmish and do it in a way that feels idiomatic, even if it's on a blurry screen. So I apologize for that. So that was the reason why I wanted to show the CO2 sensor and the VOC sensor actually doing its thing and running, is that is something that's very stable. It runs very reliably. I've run it for days at a time. And other than the sensor itself, it's a relatively cheap sensor that doesn't have compensation. So if the humidity and the temperature changes, then the sensor reading does change. And that's one of the things about this older sensor. So there are newer sensors now that actually have a humidity and temperature, and I think some other sensors built into it, so it can do a compensated value. So in those environments where you're running a machine, that the machine itself is giving off heat as well as the volatile organic compounds, so that it will continue to give an accurate number because it's compensating relative to the humidity that the sensor is changing, and therefore the value is being relatively consistent. So that's going to be part 2 of that project, and using a sensor that actually has the compensating values, and then also looking at getting the temperature and humidity and other things and putting that on the display as well. So I want to move on now to I guess you could say the meat of this, which is looking at the solar project. And I'm going to actually see if I can expand this a little bit. Is that okay? How's that look?
It's still blurry, but let's go with it. It's
sorry
big,
about
it's big enough that people can read it, I think.
Yeah, maybe there's something about the OBS settings that I'm just not, I haven't set to make the right, in the right resolution whenever it displays, because it should be displaying in 1080p. I thought I'd set that. So, so the basic idea was to create an ability for a solar panel to be able to find the sun without actually having a light sensor. And the basic idea is that a lot of these projects that do this work end up having a sensor that's actually arrayed with the solar panel, and then looks for a hot spot, essentially, which is the sun in the sky. And they have 2 sensors that are aligned so that they have to have equal voltage to them, and therefore it knows that it's pointing at it. So the idea is that it's great as long as it's sunny. But if it's not sunny, then you end up seeing the solar panel kind of chase the sky a little bit, because the clouds occluding the sun means that it doesn't actually know where the sun is. So instead of actually using a sensor method for finding where the sun is, I wanted to use a calculated method. And for that, I ended up using and finding the coordinate sharp library and doing a little bit of calculation on my own, and going through several different versions of that in the process of figuring out the most accurate method of actually getting the values that I need for making sure that for the time and location and the azimuth of sun, that I know what position the solar panel needs to be in order to be perpendicular to the sun. So I was going to go basically pull this together, and actually probably should just go ahead and again start with the actual thing that that actually shows what's going on. I'm going to actually send a message to the solar panel that it's going to turn it on, and then tell it to go to a new angle. So I'm just going to tell it to go to 20 degrees for this. You actually see here, this is my mobile phone that I'm mirroring on the screen. So I'm just sending it a text of 20, and then I'm actually going to go ahead and start this and run this in a console. So give me just a quick second. So what's going to happen is it's now at like a 12 or 15 degree angle, and I'm going to send it a new angle that will then activate the motor and turn on an LED to actually reposition the solar panel. I'm going to run this in a debug mode so that you can actually see what's going on, at least given the blurry screen. So right now I'm just going through and if it won't do it, then we're just going to go ahead and go through and I'll just send that command from here. Let me just do that. Yeah, there's a US, of course, this is in the world of live demos, which you should never ever do. And so I am going to send this command from here. So that's basically sending the number 20 to the input of the Bluetooth that then converts that to a float number and sends it into a function and says, regardless of where you are, go to 20 degree angle. And so it's going to continue to evaluate and do that loop until it gets to that, and then it will stop. And so that's the magic, that's the outcome. And the basic idea is like, instead of me sending that over Bluetooth into the device, there will be a daily function that starts in the morning before sunrise that goes and, sometime before sunrise, it wakes up, it finds out what time it is, and then runs this calculation through Coordinate Sharp and gets all the values back for when is the sunrise, when is the sunset, which is when the panel opens up and when it parks in the evening. And then when solar noon is, which is when it will be at 0 degrees and perpendicular to the sun, and then plus or minus about 25 degrees. And I use 22 to be safe because I didn't want to overrun the way that I'm positioning the solar cell. And then as the solar cell is, positioned at a partial angle, it's not actually chasing all the way to being perpendicular to the sun at all times. The reason is that in the early morning hours, you're not really seeing that much difference in the amount of power that it collects. So there was a large commercial installation in Australia that actually did an analysis of this, of fixed panels versus the panels that were actually chasing the sun. And that the trackers were getting 100% more power in these early morning hours, but because you're only collecting 7 watts in the earliest hour, then you're collecting 14 instead of 7, which isn't that much of a difference. So instead of going through the maximum extremes of moving it so far to possibly cause fouling of the mechanism, causing higher maintenance costs, they actually changed it to do less of an angle change so that it's only doing part of that. And then as soon as the sun is perpendicular to it, then it's tracking through that limited range that it was doing. And so that meant that the maintenance costs were lower and they were still getting all the benefit of the additional power of having the sun being directly perpendicular, the cell being perpendicular to the sun. So I'm using the same kind of theory with a different mechanism that has a limited motion of range. The idea is to do it with a cheap CNC motor. And the idea is that since they're commoditized and available everywhere, that you could make something that could be produced in quantity for like a mobile project or for some installation that's relatively small. And then eventually, if it became something that was commercial worthy, then of course, just get a bigger motor. So when you look at the side view of this board, you can see that down at the bottom of this image is the motor that's actually doing the work. And there's a threaded gear that kind of transposes underneath the solar cell, and it moves either clockwise or counterclockwise to raise and lower the solar cell. So the board that's over there on the edge of the solar cell is the brains of the whole operation. It's actually measuring in real time the angle that the board is at. Now, eventually, when this is a finished product, it's going to be inside of an enclosure, and that enclosure is going to be underneath the solar panel. So for now, I'm actually flipping the value that's coming out of the calculation by 180 degrees because the board is actually inverted to the position it will be when it's actually underneath the solar panel. But for now, what's essentially happening is we've got multiple sensors doing things, and right now we're only using 2 of the 4 that are there. The 2 that are being employed are the accelerometer, which is that single blue device of, I apologize, the labels are too small. The red one in the center is the actual driver for the motor. And those 4 wires that are coming off of that driver are the charge for the coils to either run counterclockwise or clockwise of the CNC stepper motor. So it's really sending a series of pulses to the motor to get it to move. If you've done 3D printing or CNC control, this is exactly the same mechanism. This is the exact same driver that's actually used for a lot of these projects. The two other boards that are off to the side that have the large lugs on them are circuit boards that are designed to analyze power, amperage, voltage, in order to be able to see what's happening within an electric circuit. So this will eventually become high side sensors for two solar panels, and I'm going to have one that's a control that's in a fixed position that doesn't change position, and right next to it, this solar cell that actually does change position and follows the sun. And the idea is to capture that data, send it to a database, and then be able to analyze and look at the delta and the difference of power that's collected for the two solar cells. In the project from this Australian commercial solar installation showed that the difference between fixed cells and these cells that are moving was around a 15 to 25% difference in the power that was collected. So it's a pretty significant amount of additional power that's collected for this. So I wanted to evaluate to see if that was the case, because I'm not moving through quite so much a broad range. And of course, I don't have as much sunlight as they might have in the deserts of Australia. So I will probably also put a light sensor on this so I can actually know the amount of sunlight that's occurring. So when you see fluctuations, that we can attribute it to sunlight. And there will be one more thing that I'll be adding that's not a sensor, but I'll be adding an actor that actually goes out and looks at the Open Weather API and finds out if there's winds that are either coming or winds that are currently prevalent in this area that are above a certain number of miles per hour. And if so, have an override that parks the panel so that the panel doesn't get damaged. So, but for now, we're really just focusing on sensing the angle of the panel and moving the angle of the panel, which you've seen the initial demo of. So it's just the driver and the ADXL345, which is the accelerometer. So we go and we look at the code, and I make sure I'm looking at the right window. One of the things that I do in the helper functions, and this is about calculating what's coming off of the accelerometer, is that everything's reported in radians, and you get X, Y, and Z. In order to know the angle of Y, which is the tilt of the circuit board itself, you have to get the inverse tangent of X and Z, and then apply a radians to degree conversion. And of course, I do a subtraction out here of minus 180 that I'll get rid of whenever I actually park the board inverted underneath the solar panel. So this is the first real interesting thing that it's like, I don't think I've ever done an inverse tangent of anything before, and I had to look it up. So this is one of those things that, like looking at the, there's an actual calculation to look at in astronomical algorithms. It's the actual algorithm that you see in the document is very close analog to what you would actually see in the calculation of the code. And so having F-Sharp's ability to be able to represent this academic thing in a way that actually surfaces all the way out to controlling the way a real physical device works in the side effect world, to me was a really nice thing of like going from academic to the tangible. In the main meadow app, there are two functions that are really doing the most work. And I will go ahead and just pull this out of the way. And these are two different tasks that are running independent of each other for a couple of different reasons. One is the control task is like, I don't care what anyone else is doing. I'm going to run this task that says I'm just managing the angle of this solar panel and the accelerometer and what's happening. The second one is a monitoring task, which is looking at what the angle is at and then sending a flag that they're both paying attention to say, do I continue moving the motor? So the monitor stops the motor. There is a problem within the amount of turns that I'm putting in the linear actuator, and this shows up here in this particular function that's basically for a correction of overshoot. So you'll actually see sometimes it'll go past the range that I want it to stop at, and it will actually pick that up, and then on the next time I bring it back in. And so I'm working on actually getting a bit more dynamic with as you approach the actual destination, that it will actually slow down so you don't end up doing overshoot. But for now, I just have this compensation in it that will just bring it back if it overshoots the position that it's looking for. So far, it's been pretty well behaved because the controller for the stepper driver allows you to divide down the amount of of turn that you put on the motor. And these just happen to be values that work well for the range that I have it in right now. Eventually, when you get into very low degrees of angle, like from 0 to 5 degrees, or the very high degrees of around 25, those numbers will change. And so eventually there will be some logic that will be built around that will sense of, oh, I'm at this position, I can go this fast, or the difference between where I am and where I'm going is so large, I can actually move very quickly through some of these early values. And then once you get to a small delta between where the position is currently moving and the destination, to then slow it down into smaller increments. So this is very much like running if you see this, if anyone's worked with 3D printing or with CNC machines, that you'll see the motor will do some gearing down as the pulses change their cadence and intensity.
Or something
So
like
that's
the
what
idea.
these step divisors and the speed divisors actually do for you. There was a question?
So it's you're planning to do something like the ID controller.
I'm sorry, I don't understand.
So you're planning to do something like a BID controller.
Yeah, I still don't understand. I'm gonna have to turn you up a little bit.
1 second.
Or maybe you can write the question into the chat.
Yes.
Yeah. Let me see if I can pull the chat window up. Here we go. So something like a PID controller, exactly. So one of the nice things about the constellation of drivers that Wilderness Labs put together is all of these SparkFun and Adafruit and other brand controllers that have these pinouts that have been used for other formats for Raspberry Pi or for Arduino. They have support for. So you can drop these boards in and then just be able to address them, in a .NET way. And so a lot of the off-the-shelf components that are very commonplace for you to be able to buy online, wherever, you can pick up and do that. And that's exactly what I've done. So you can get an off-the-shelf PID controller. There's, of course, these off-the-shelf sensors. And the display that I use, this round display, is called a GC9A01, which is basically just a cheap smartwatch display that they use for other stuff. So really nice thing about this is you can go and address these devices. And one of the things I'll be doing is going to a higher power capability a driver that can actually handle up to 2.5 amps of current, and it's pin compatible with this one that's an older model that only can handle 1 amp per coil. And so that's part of the piece dividend of like all the commoditization of 3D printing and the CNC devices and all the other motor projects and all the maker spaces that are out there, is that you can take and leverage these devices now and be able to take and attach them to a Meadow and be able to drive them with .NET code, which is really exciting. So the business end of the task that basically kicks off these two exercises, both the monitoring task and the motor driving task, actually happens within this function. And this is where the value comes in from Bluetooth and gets passed in through the characteristic. And it comes in, it's a text value. Again, this is a weird thing where Bluetooth is weird to begin with, but it's the implementation that is currently extant within the Bluetooth server for Wilderness Labs Meadow is it can accept an int32, a text, or a Boolean. So there are other formats that you can set up, and maybe I'll end up doing that to be able to do full hex and other things that allow you to have a more nuanced and less transformy kind of thing. I have this thing that always scares me whenever I have the a coerce there where you're, of course, here I'm actually doing it with a triparse, which is okay. Then on the sending side, whenever you're on the Bluetooth device, that's actually the client device that's sending it back to the Bluetooth server that's sitting on the Wilderness Labs Meadow, you may need to be sure that you're minding the store. That eventually, that makes me feel a little itchy. I want to be able to have a well-controlled thing of knowing that I'm sending something over in a format that I know it will take an input. So that's something that will get worked out over time. For now, this is the Wild West. And so we're in the world of actually doing, coercion and casting. And so far, I've been good about punching in only numbers and not something that's weird. One of the reasons why I have these little catches here is that if I end up doing something that doesn't actually coerce to a double, then I at least see something coming back in the console. So if I fat finger something as I'm punching into the phone, like, oh, I hit the letter O instead of the number 0 or something. So what this does then, of course, when it does match it and it has the angle, it passes the angle in to run these two tasks independently. So it's just saying, hey, just go and run these two tasks. Eventually, I want these to be actors or agents. I want them to be something that actually acts within either the Elmish loop or it spins out from the Elmish loop as a side effect, or runs with Akka.net. So those are two of the options that I'm evaluating right now. But for now, I still have this thing that's running that allows kind of that feel of these two separate tasks that are running. And when they do run and emit into the console, then you can kind of see what's going on screen. Now it works reliably enough that I don't have to worry about it as much. I just throw a number over and I know that it's going to do it. But eventually, when it gets into doing those more nuanced motor control functions of slowing down when getting closer to a given destination angle and so forth, that will become really handy. So this is that weird world of kind of between this purely Wild West. I'm just throwing mutables everywhere. Like the early version of my CO2 project, there's just tons of mutables everywhere too. The only place where mutables are there is where they're absolutely necessary, and everything is really managed within the model itself. And one of the concerns that I had with the Wilderness Labs Meadow that ended up not being a concern was, how does the GC handle this, the immutable, the model basically getting updated really rapidly. And the disposal of that, does it overrun memory, or the possibility of something just when you're running mono on top of an RTOS that's not a full desktop operating system, you kind of have questions about that. So we're still kind of testing that out, but it looks like it's just handling it without even breaking a sweat. So the safe world of being immutable and using all of those mechanisms within the type safe and statically typed world of F# is really readily available, even all the way out to the edge on this little microcontroller that's less than the size of your fingernail. So let's talk a little bit more about the solar calculation and the things that I did in the process of figuring out what, how to get an accurate calculation of what I call a sundial function. The sundial function is, the sun is at a certain angle. What time is it? And it's that weird thing of like, I want to say that the sun is 22 degrees off of solar noon. What time is that? So now I'm going to create a tuple that is at this time or date time, be at this angle. Then I'll set up quartz.net and a function that basically pulls that up at the right time and throws that number at that function that then triggers the motor and the monitor for it to reposition. So the idea is that you have this kind of message-driven or EDA architecture where the function that's receiving that command, whether it doesn't care whether it's coming from this Bluetooth control of a user saying, I want you to go to 15 degrees, or there's something that's happening from quartz.net that says, go to 15 degrees. I don't care what angle you're at now. This is part of being recoverable. Like if the device has, gone to sleep for some reason, if the power has been cut, or if there's been a reason for it to park and for it to go into a maintenance mode, and then it kind of needs to wake up and reestablish state, it can go and find out and figure out what that is. So the device can know what time it is. And of course, I'll give it a configuration file or send data over from Bluetooth to say, this is where you're located or where the phone is located. And eventually there can be an actual sensor on the board that's for GNSS or GPS, where it can find out where it is. It can be fully independent and self-standing. For the purposes of this, I wanted it to be relatively, I guess you could say, quick and cheap. And the idea is to manage the cost of it, as well as because we want the running cost of the device to not be more expensive than the additional power that you collect over time. But the idea is like it can wake up from an unknown state, and without too much interaction from the outside world, it can rediscover and reestablish its own state. So it can figure out what time it is. It can figure out with a GPS sensor, it can also know what time it is. So that's kind of one of the things that makes it really, truly freestanding. But if it ends up having access to Wi-Fi, then it can go and talk to the Wi-Fi endpoint, and it will eventually get time from talking to one of the NIST sources that says, the time now is, and so on and so forth. Once it knows its location, then it knows time offset, and it also knows how to make some of the adjustments, because every one of these calculations has a latitude and longitude component to it as well. So it needs to know its location to be able to send pass the data into the function. And it doesn't change very often, of course, but the idea is that it just needs to be a known value at that startup when it's kind of coming back from an unknown state. Once it's done that, it knows what time it is, then it goes and we'll check that list and say, oh, the solar panel should be at this value. So if there was ever this intermittent power outage, they can go back and restore its state within a minute or so. So that's the long story of knowing that the device has to know its state. And for each one of these calculations, you're not only sending it a date and time, or at least a date, but you're also sending in latitude and longitude. I'm going to switch over to this thing of looking at this PDF document of this book called Astrological Algorithms. And this was referred to me by the person who wrote the Coordinate Sharp library, who said, if you wanted to figure out how to do this more accurately, this is the place to go do it. So in the process of creating an obliquity of ecliptic and equation of time function that wasn't present in the Coordinate Sharp library at the time, I went to this and actually just started pulling things out and started reading. Of course, I haven't done trigonometry since, I don't know, college. And I probably have done some somewhere at some point, but it's like, this is like you're living in this world. But one of the things that was kind of a comfort was looking at this algorithm, looking at this example within the book, and then being able to go to say, you know what, I'm just gonna do that calculation. So here is that thing, and I just copied it and did the rest of the other functions, and of course a little bit of Q&A back and forth with the author of Coordinate Sharp, and came back with this function that actually looks very much like the algorithms that are shown in that book, but are here in just pure functional form. So you just hand it a date time and it gives you back the equation of time for it, and it uses the obliquity of ecliptic function. It steps out to it, does that calculation, and brings it back in and uses it to finish the calculation. So it turns out, and I'm going to just do a little bit of, let me grab all of this and just send this to. So I'm putting all of the calculations in the F-Sharp Interactive, and I haven't actually done the calculations yet. So all of that code is in there. So this first version of this thing where I've built the obliquity of ecliptic algorithm, I've done the equation of time and trying to get something back more accurate, it turns out that it was pretty awful. It wasn't accurate at all. And I actually ended up doing a compensation for it. Now, this is pretty decently accurate. Let's go find that. Yeah, solar calc, there we go. So I would go and do this exercise where I would get this value back and would look at, what is the max time and the min time for this, and would then go into that window and I'm trying to find the window on my desktop. So I would go to that date and say, okay, well, here's today's date, and that's the 15th, and I'm going to go look at 126.56 is what it calculates for solar noon. And I know it's really small, and I apologize for that, but that's the size of the window. But this little orange box down here at the bottom of the window actually shows 1326. So I know 126 is accurate for the solar noon that's been calculated. And I will grab this slider and move it down to the time, which here I'll say 12:30. So this is 12:32. Now, so I want 158 and 202 about for the two positions where I'll position the sun. I may go wider, but for now, those are the numbers that I'm using. So the idea is when I look at this number and I move to that time that's calculated, and of course I've got 126. Let me go in 12:32, go 126. Oh, it's a little touchy because it's such a small screen. As 128 is close enough. So that's solar noon for this area. And then to go 20 degrees plus or minus, I'm going to go to 12:30. And this is to prove that it's actually not that accurate. But this is that thing of like from a separate verification, I'm looking at 1230, and then there's this really small value again for azimuth. Again, I apologize for how small it is. It says 155. 155 is not bad. It's not horrible. But the problem is that as soon as you go further and further away from the date for which you've programmed this, the errors get bigger and bigger. And that's because of the nature of the oblique path that the Earth takes around the sun. So you have to compensate for that. So the attempt to compensate for that is actually, I did it in a second location, it's like a second crime scene. And what I'm going to do is look directly at this. Sorry. Okay. So this second crime scene is this long thing. So this is my hack for EOT. And I'm trying to actually run my cursor over it like a, so this is basically a linear function that goes through and finds what day range we're in relative to a static date that I've set, and then does a compensation for it to get it within a couple of minutes. So this is super, super hacky and super, super awful. And there's the reason why it's awful is not only because it's date banded. I've only done it for 90 days. I could do it for 360 days, 365, and then it would loop back around and would be relatively close again. The problem is this compensation is only for this location. So if I moved from Asheville, North Carolina, where I live, to Los Angeles, California, those compensations wouldn't work. So this is a really weird, awful thing. I did it, it actually does work. So when you actually do the function, you actually get something that's more accurate. I am going to skip past that because I want to get to the good stuff. The good stuff was the calculation that was done by, this is actually something that was provided in C# by the author of the Coordinate Sharp library, where it actually goes and calculates the compensation for each individual component of that time, which is the hour and the minute and the second, and then creates this. And he did this all in C# and I converted it to F#. So essentially what happens is you make a call just to this function and it calculates all of this. And he considers this very expensive and very wasteful. I don't care because you're running it once in the day and you're just getting everything that you need for the day back in that array. So this is that thing again, like in the way that my F# for the CO2 project and of course for the solar project is, it's basically looking back into C# and bringing it forward in an F# way and running it within F#. This is the same thing. So the eager load extensions and everything that's here, these are elements of the Coordinate Sharp library that's there, that's kind of that easy kind of low code thing that makes it accessible. So, and he also has some housekeeping where he's done some very strong typing in places where you can kind of trust what you're getting back. So this is a really fantastic library and made it relatively easy to, and of course the way that he writes his C# is kind of functional-ish. So if you write something in C#, you can kind of, it's easier to make the transposition over into F#. So, and of course at the end here, it's just giving back a second's compensation after it goes and does all the other functions. So here's this thing that's being calculated. Let me just go ahead and run the function here. So this is loading all the logic. And then what I'm doing is I'm getting 202 and 158 like before. The latitude and longitude is the general area of where I live, offset of 4 hours. And of course, if you're running this inside the context of a device that has system time, you're actually making a .NET call for that. You're not just hard coding it. There's the date time. I'm going to change this to the 15th just for fun. And then doing all the work and getting the values and reporting them out in the console so it can be verified. So, come on. All right. So what we've got, I'm trying to just make this large enough where everything can be seen, are verifiable, some extra verifications that are in here, but we've got the time at sunrise, and I'm going to go ahead and, sorry for all the switching. Back to this. So the time at sunrise is 7:13 in the morning. This actually shows 7:14. So that's close enough. Again, being within 1 minute is not a big issue for me, and being off by several degrees in several minutes is where things would get weird. Again, because in the summertime, the window between that plus or minus 25 of solar noon is a really tight window. In the wintertime, it's much, much larger because the sun is traversing the sky in a much wider arc. So those errors tend to kind of expand during that time. So the idea is to be accurate throughout the window. And so solar noon is at 126, and here we have in the solar sunfollower.net, it also says 1326. And the values are very accurate. And it has these secondary validations of, oh, this is that amount of time between 158 to solar noon and solar noon to 202 is 48 minutes. So again, that time would expand as you go to later in the year. I saw when I started this project, it was in July, and it just happened to be on one of the longest days of the year. And it was weird. There was actually a day that's longer than 24 hours. I happened to do this work on a day when the day was 24 hours and 4 seconds long. So that's that weird thing of the obliquity of ecliptic, and the equation of time function is to be able to compensate for where the Earth is on that orbit and about its, its revolution and its position around the sun. This particular method, even though it doesn't directly use EOT and the obliquity of ecliptic, it's still very accurate. So it's like it's using a different methodology to get to the same result, and it happens to be accurate. The secondary benefit of this is it's not only accurate for any time that I do this without any compensation whatsoever. It's just a calculated value coming out of coordinate sharp. But it also means that if I change location and getting the date offset and everything else correct, that it works for anywhere you go. So if you take and put this installation somewhere like Portland, Oregon, and you put on your phone that what your Latin long for that is, or you pick it up off of location services on your phone and send it to the device for it to write in a config file, then it will just work and work accurately. So the idea, I don't want to be too over fastidious about the accuracy of this device, because it's the generalities are, it's not like it's a clinical device or something. But at the same time, you also want to be sure that the numbers that you get back for measuring the advantage of having a positioned solar panel versus a fixed solar panel, that you're maximizing that as much as you can to be able to show the value of it and show the additional power that you can collect from the solar cell given that angle. So I'm not just positioning this at 180 degrees and then 202 and 158. I'm actually starting at 158 at sunrise and waiting until the sun moves around to that position, and then a few times changing that position eventually until it's at solar noon. Now the number of times that I change that position between 158 and solar noon in the summer will be relatively few. It'll be like maybe 2 or 3 position changes. But in the wintertime, because the angle is much longer, or actually the time is much longer, the angle is the same. There will be more positions that I'll pick because it'll be over an hour and a half, as opposed to happening over maybe 30 or 40 minutes. So even the time of year when this is happening and the additional positions that I'm picking between those things that I'm getting back from the coordinate chart library will be something of a point of experimentation to make sure that the solar panel is always in that most advantageous position to be able to collect as much power as possible. And I imagine that being more position changes in the wintertime because of the lower angle and the desire to be able to be more extractive of the sunlight that is available for the angle of the sun and the position that it's in during the winter months. So this is kind of the sum total of what I'm working on. Is eventually, right now, I'm just sending a command directly to the sensor and making a change to the position. But eventually I want it to be able to wake up, smell the coffee, smell what time it is over Wi-Fi, and then be able to pick up from the config file that I would write from my phone on the local device to be able to know where it is, and for it to just be able to wake up and find the right position to be in. So there will be a use of the Quartz.net library. And eventually, if I end up going to Akka.net, then Quartz is kind of involved in that for some of the scheduled activities that that actor model supports. But right now, I want to use Elmish and use Quartz.net directly. And then go through the process of actually measuring this over several weeks and finding out the delta of the amount of power collected from the fixed panel versus the one that's moving. And that's the end of that experiment. So over a certain period of time, finding out if the advantage of that 15 to 25% additional power that's collected for the single axis control of the solar cell actually does prove out, then it makes it matter for whether or not this can become a commercial application that actually has that kind of monetary benefit. Everyone that's doing all of this work within the solar sphere is thinking of it in terms of, what is the payoff and what is the amount of time for the amount of money that you're putting in for some of these additional things to be able to move the solar panels around. I saw one dual axis controller that actually costs like $3,000 to move something that's a 400-watt collector. Paying $3,000 for a thing that makes a minimal difference doesn't make a lot of sense. The total out-of-pocket parts for this is about $150, which is 1.5 times what the solar cell itself costs. So that idea of like extending the payoff time of the amount of value that you get from the solar collected versus the total cost that you have for the mechanism also has to be paid off over time, that you want the mechanism to be robust enough that it will last for a while. So I've only tested this mechanism for several days at a time, but for the actual microcontroller itself. And eventually the CNC motor is built for the inside, it's not built for the outdoors. So there will need to be some additional engineering that happens with that. But the exciting thing is being able to work with F# on the backplane in terms of managing the database and managing the event store and rendering the charts and the things that you want to look at the data in aggregate, and being the same model that you use for the code that's actually all the way out on the edge. So the mobile device is running F#, the edge device is running F#, and the backplane is running F#. And so even though it's a lot of mental domain, it's really kind of, I guess you could say full stack, full bore. But the cognitive control and burden of that is, focused in being, well maintained within the F# stack. And that to me is what makes this really exciting. Is back in the day in the 90s when I started doing this, the world of working on the edge with the satellite microcontrollers was wildly different than the world of working with, managing a database in like VB or whatever I was doing at the time. So the fact that we have this cohesion now that and the semantic consistency that is available throughout the stack, to me is really exciting. And that's kind of what I wanted to show. So that's essentially the sum total of what I have for today. So thank you so much for your time.
Man, Houston, thanks. That was super awesome, super interesting. Are there any questions from the audience?
I'm just going to run.
No.
I have
All right.
one. So you are looking at this as a potential product that you can basically offer in terms of offering this to people who want to benefit from solar energy, clean energy, and how to get the best of the sound. Basically, is that your idea?
Sorry, the motor was running off as I was repositioning that. So the long answer to that is yes. And at a minimum, I want of course, the code is all open source. You can look at the mess that I've made, and eventually there'll be something that I think will become an Elmish template for Wilderness Labs Meadow, and become a boilerplate that's was inspired by Jordan Marr, who I wish could be here. He did a lot of this initial shifting into the Elmish model for the Meadow from a cold start without having a device in front of him. And I just made a few minor changes, and to me, it still looks like magic. The idea is to have these kind of boilerplates available to people. For the commercial product itself, I do have a patent application out for the mechanism, which is the reason why I'm not showing too much about the mechanism. I've already have ideas about the ways I want to change it. Right now, it's one of those things of, how do you make it inexpensive enough and robust enough? It's that thing of having the kind of the payoff be there in the long term. Most of the time when people put in a large panel installation, they want it to be there for 20 years. So those are the kinds of things that you have to think through. When I worked for Bob Moog, it was definitely, we're building musical instruments that we want people to have 20 years and to pass on to somebody or to be able to resell and so forth. So still looking at it from that perspective, and I'm looking at some different manufacturing techniques for that. So 3D printing matters. Additive manufacture, there's a place here in North Carolina that actually does additive manufacturer for titanium. Now it's for high-end bicycle parts. But I looked at it, and it's amazing. These are very high, these are off-road bicycle parts that are for people that are professional racers. And they 3D printed the part with titanium. That to me is just like mind-boggling. Now, it'd be really expensive, but at the same time, now thinking about doing a very specific build with a specific weight characteristic and performance characteristic in 3D with additive manufacture does change the calculus a little bit. So definitely thinking about the commercial applications for it. And it's a lot of exploration and discovery and creativity in that process.
Because yeah, I'm asking this because my neighbors here in Spain, most of them are investing in solar panels because here there's a huge incentive from the government to start trying to provide your own energy, and you still need to get some get some permissions from the electrical companies that they did all the hard work at the beginning to get the light, the electricity to your house and that stuff. But yeah, I am also looking at that. So definitely, it's something that I would love to be able to control, and save and to store some energy from, I live in London, but my house is in Spain. So it would be amazing to be able to control all of that by a device that is
Right.
from a different country.
For sure. And the nice thing about having the theory about what we're living with in North Carolina is the same thing with the power company, where it's a little bit tenuous in terms of, going fully off grid. We're fortunate that my partner and I live in a place where it's on the same substation as the local regional hospital. She hasn't been out of power in 16 years. So it's like, it was not so much about that level of resiliency, but we also want to have just that financial independence of actually collecting our own power instead of just giving it over to this monopolistic company. So it's a relatively small house. It's something that's built for a small family. It's not something like a typical American mansion where you have 2,500 square feet of floor space and therefore have a large roof area. So the idea for me would be to take and modify that fixed array that you have on the roof and be able to take and then add on to the mechanism that can then reposition the panel to increase the footprint of the solar cell ostensibly. It's like if you're collecting 15 to 25% more solar power for the same number of cells, then it's like expanding your solar array by 15 to 25% to be able to bring the power in. So part of it is reducing your power demand, but the other part of it is, being really efficient in your collection. And we're also in the mountains. And so our sun rises a little bit later than most people. Fortunately, the early morning hours don't really provide that much power, but at the same time, I wanted to be able to have the solar cell, as soon as it comes across the top of the mountain that's on our horizon, that it's collecting that power as efficiently as it possibly can. And there's a lot of people that are like that. So I think there's room for a mechanism, and there's a lot of people working on this to be able to, work with a more efficient power collection over a smaller area, not only to be able to work at a vacation home or a beach home, or to be able to apply to like a recreational vehicle or camper, but also just like the intensity of the power that you can collect then means increases your ability to be independent, whether it's for adverse conditions or it's just, again, you want to not just be part of some, commercial mechanism where they're polluting the atmosphere because the power plant is powered with oil.
Imagine you have electric car where you can, you have a chargeable, how do you call that? A chargeable, what do you call it? Yeah, you have a charger in your house that you need to get the electricity. So you can get that from the electric company, or that can be, in places like Spain where we have, 40 degrees and almost 44 degrees every year. So
Yep.
You're going to get a lot of sun. No many wind, but the sun, you can have a lot of that. Most of us, I don't know, maybe 4 months, basically.
Yeah. That's the holy grail, really, is to be able to have your car or vehicle powered by the sun, the same way that your house is powered by the sun. And that requires you have to have two-phase power, which means you have to have a lot more equipment, and it means the recruitment cost is longer, but that's getting a lot cheaper. as it's, they're figuring out more intelligent ways and more efficient ways to make that technology. A lot of that has to do with actually making the time for software engineering more approachable as well. Like when you have these tools that are readily available to you, then bringing it to market is much shorter. It's the same way with that additive manufacturing and the CNC machines, which is really subtractive, but the ability to manufacture things that doesn't require injection molding and the other mass manufacturing techniques is you can make it economically feasible to do something in a quantity of 100 or 1,000. Whereas before, you'd have to be at 10,000 or 100,000 before it could be really commercially available. So the meaning of what makes something commercially available is changing too, because additive manufacture is going to make a lot of this much more approachable than it was when it really had to be a General Electric that had to do it before it could be done.
Yeah, sure. Thank you.
Yeah.
All right. Yes, thanks again, Houston. You are more than welcome to do this a second time with your next projects. I will stop the stream now, and yeah, see you.